Hello. So, at last we have reached in our last lecture or maybe the last presentations actually, which is dealing the main problems in synthesis of modified nanomaterials. So, what we have done till today is that we have tried to give a brief overview about the surface engineerings, what kind of problems generally we are facing, then how we are trying to modify those surfaces, then in terms of nano composites or nanofillers, how we can make the modification of this kind of nanofillers, nanomaterials. Then we are trying to enhance the properties in terms of mechanical properties, maybe the thermal properties, maybe the optical properties, maybe the biomedical applications, or maybe some kind of other properties too. But still when we are using this kind of materials, still we are facing certain kind of problems. As you know that always our demand is increasing, our demand is going on. So, when we are trying to make today, tomorrow we are trying to enhance its properties, and not only that, our main aim or main motto is that how we can enhance the properties within a short time, so that our material should be less expensive, not only that its lifetime will be increased, not only that it can be sustained into different environment. So, there are several numbers of thinking actually, or maybe that research we are doing, that how we can optimize the process, how we can use these kind of materials for the various applications. But till today still we are facing certain kind of problems. So, in this particular lecture, or maybe that rather we can say that in this particular last lecture, just we are trying to show you that what kind of problems generally we are facing, then we are trying to modify those problems, but still we are lacking into some cases where still the research is going on, and people or maybe the scientists are trying to enhance those properties, or maybe that develop some new materials so that we can get better properties than today. So, in this particular case, first what the thing we are going to discuss, that what is the main problems generally we are facing when we are preparing some kind of thin films. So, before going to make the thin films, just one for our understanding, just we have to know that what kind of parameters actually it depends upon preparing the thin films. So, first is that techniques which are to be used. So, techniques means there are n number of techniques which I have discussed throughout my lecture in brief. So, first we have to choose by which method we can make our thin film, so that it can give the better properties, it can enhance its properties, not only that it can stick to the surface itself, or maybe it can sustain into different environment, or maybe that different temperature onto the different substrate, or maybe some different conditions. Next is that processing temperature and pressure, that while making this kind of thin films, what kind of temperature I can put, what kind of pressure I can put, because I will show you that at different temperature and the different pressure the material structure is totally different. So, when the material structure is totally different, the material property is also totally different. Next, what is where I am using this kind of materials, whether into the some inert environment, or maybe some kind of into some gaseous environments, or maybe in kind of toxic environment, or maybe into the vacuum chamber itself. So, that is also one kind of prime factor, because my material should be well conversant to this particular environment, because when I am making certain kind of materials, I do not know that where the material is going to be used in India, or maybe whether that material is going to into some south poles, or maybe some USA, or maybe some other places. That means that material can be used into some hot environment, into some high temperature environment, into some high pressure environment, or maybe I can use this kind of materials at the top of the hill, I can use this kind of material under the sea. So, that pressure of that particular material can be changed, or maybe that environmental condition of that particular material can be changed. Then the next one is that the source of precursor. Source of precursor is nothing that from what source I am making this kind of materials. So, what is the source of that particular material, whether that material can be sustained into different environment or not, whether that material can be having the good life or not. Then the speed of rotations in terms of spin coating, that means what is the processing conditions of that particular material, how much rotations I can put, how much pressure I can keep, how much temperature I can give to prepare this kind of materials. Not only that, time durations, that how much time it is taking to make the final product, whether the reaction will be very short time, whether the reaction will be for a longer time, because I have shown in my some previous lectures also, if I increasing the reaction time, automatically the thickness of that coating or maybe the thickness of the thin film can be increased. So this is also a vital input parameters for making the thin films. Not only that, the rate of depositions, that how fast the material is depositing or maybe the how slow the material is depositing, because it depends upon so many properties, that addition of that particular material, how fast it is, whether the addition properties of the substrate is very high so that it can easily absorb the materials, or maybe the materials can be deposited easily onto the substrate or not, or maybe that how slow the deposition rate it is. So depending upon that, the thickness of that particular thin films can be increased or maybe the decreased. So here we have given certain examples. So the examples is for the iridium oxide thin films formations via ALD process or maybe the atomic layer deposition process. What in this particular FECM image and in this particular atomic force microscopy image, just what we are trying to show, that if we increase the temperature, means the preparation temperature of that particular material, so how the surface roughness of that particular material is going to be changed. So in this particular case, when I am applying the 100 degree centigrade, you can see that some kind of smooth surface of this particular material, but still when I am increasing my temperature from 100 to 120, then 140, then 160 and 180, so how can you can see that how the material surface is totally changing. That means from the smooth surface we are trying to make the rough surface of this particular material, and same thing has been proved by the atomic force microscopy image of this particular sample at different temperature. So from this particular temperature, you can see at around 180 degree centigrade, the surface roughness value has been gone up to 4 nanometer. So that means initially it was 0.3 nanometers. Then how the temperature is affecting the surface roughness of these particular thin films. Next, there are several types of problems we can face during the fabrications. First one is that uniform film thickness, that is the vital parameter, because every time we are talking about the coating, but coating properties also depend upon the thickness. Not only that, the deposition rate of that particular material onto the substrate itself. So first one is called the uniform thin film thickness. So in this particular case, we have done the cross sections of the solar cell materials, and the top of that we have done the coating by its gold, but from this particular image you can see that coating thickness has been varied into different zone. That means non-uniform film thickness has been observed for these particular materials. Then we are trying to give the adhesion properties, because that is also the biggest and foremost parameters for any type of coating materials, because when I am depositing our material or maybe that coating material onto the substrate itself, then what is the adhesion properties of that particular material, so that it can stick easily to the substrate itself, or maybe if the adhesion properties is not good, simply it will come out from that substrate film. So here also the same thing, I am using certain kind of substrate, then I am doing certain kind of coating materials over there, but still the adhesion properties is not good, so that you can see some kind of coating materials has been detached from the substrate side. So gold thin film on the ceramic substrate is the example for this adhesion problem. Then another one is that crack formations. So when I am doing our coating materials or maybe the coating onto the substrate, then after drying, when I am trying to use this kind of coated materials, maybe there is some cracks or maybe that pores can be generated at that particular point. So that actually taking place, that some kind of crack formations. So here we are trying to show some kind of cracks in the titanium dioxide thin films. So crack has been formed in that, and we have seen this kind of phenomena by doing the FECM or maybe the scanning electron microscopy images. Next, damage thin films during etching or transfer one substrate to another. Yes, because sometimes what happened, I am using or maybe I am coating my materials onto some substrate, because whatever the actual substrate I need, maybe that coating cannot be possible for that particular purpose. So, what we are trying to do? We are trying to do the coating onto some suitable substrate, then simple after coating I have to take out that coating material and I have to put onto my desired materials. So, during the transfer also this kind of problems can be occurred. Not only that, the film depositions on the reactor walls, that is also a very vital parameter or maybe very common problem where we are facing this kind of problems. So, how to solve these problems? So, still as I told already initially that still scientists or maybe the people are trying to modify this kind of problems, to solve this kind of problems. Maybe up to certain level the problem has been solved, but still a long way to go to solve this kind of problems, because there is no end of preparing any materials, so that when we are trying to make the complex materials also the problem will be complex. So, we have to think those complex problems, we have to modify these problems, and when we are trying to modify these problems, maybe some problems can be solved, maybe some will be still unsolved. So, the how to solve this problem? First is that uniform thin film can be obtained during optimized parameters. For example, in case of spin coating techniques, the higher of spin rate, longer time effect, the film uniformity. So, this is one kind of parameters or maybe this is one kind of requirements by which we can increase the thickness or maybe that can get the uniform thickness of that particular material, but still this remedy is not same for all. Maybe I can use some kind of materials tomorrow where I cannot get the same thickness over there. So, still scientists or maybe the people are trying to modify this kind of problems. Here the substrate should be cleaned by etching process, chemical etching, plasma etching or maybe the ultrasonic etching the surface to prevent the peeling off. So, by doing the etching process we can enhance the adhesion properties, because when I am trying to coat our coating materials onto the substrate itself, if the adhesion properties is not, material is good, so what will happen, or maybe some kind of oil or maybe some water molecules are present, simply the coating material will not stick with onto the substrate itself. So, what we have to try to do, we have to make certain kind of rough surface over there, or maybe some water molecules or oil molecules we have to take it out, or maybe there is some dust particle are present. So, we have to remove those dust particles so that our coating material can stick properly onto the substrate itself. So, here we are trying to show some kind of peroxide thin films fabrications on each glass substrate. So, first we have done the etching of that particular glass, then we have deposited this thin film onto the glass substrate itself. Here some kind of cracks free fabrications of thin film using surfactant such as polyethylene glycol, PEG and the ethylene cellulose here. So, what we are trying to do, we are trying to use some kind of binder materials so that that coating materials will not will be crack free, and when it will be deposited onto the substrate itself there will not be any formation of crack or pores will be occurred. So, here the cracks free fabrications of TiO2 thin films using the surfactant, that is the ethyl cellulose. So, here from this FESM image you can see that there is no formation of cracks or maybe that pores has been taken place. So, here while we have already discussed about the micro encapsulations also, we have discussed that how we can do the micro encapsulations, how we can do the coatings of these particular micro encapsules. So, in this particular case again we are trying to see that what the problems generally we are facing at the time of preparation of the micro encapsulations. So, before going to start, first we have to know that what are the major elements in micro encapsulation process. So, first one is called the core, then wall, then micro encapsulation process selections, capsule post treatment, capsule substrate interactions, storage of core into wall material, release and reaction phenomena and the product performances. So, these all are the major elements in microencapsulation process. What are the factors that should be considered during the microencapsulations? First one is that core is solid or maybe the liquid, solubility characteristics of the core, reactivity of the core with wall materials and solvents, size of the desired capsules, method of attaching the capsules to the desired substrate, method of core release, process and product economy. So, first we have to make certain kind of coating materials or maybe the core materials. On top of the core we have to do certain kind of coating materials, then the whole materials I have to put into some thin films or maybe some into some functionalized groups so that it can be attached with the substrate itself. So, These all are the factors that could be considered during preparations of the micro encapsulations. But while I am taking this kind of parameters, maybe I can face certain kind of problems. What are the problems generally I can face? The number one is, one of the most different technical problems occurred in micro encapsulations is to control the properties of the capsule wall. So that is the vital problem generally we are facing now. A common problem to many micro encapsulation process is the agglomeration of capsules during wall formations. As the wall materials change from liquid to solid form, they often go through a sticky stage which makes the agglomeration difficult to avoid. So this microcapsulation size is very small into the nanometer range, and what we are trying to do, the coating material, first initially it will be liquid, then it will form the solid. So while it will transform from liquid to solid, always there will be a stickiness in between that. So there will be agglomerations in between the capsules. So that is also one vital problem generally we are facing. Next, the evaluation of capsules and capsular products is sometimes as problematic as synthesis of the microcapsules. This is also one vital problem over there. So what are the solutions of these problems? How we can solve this kind of problems while doing the micro encapsulations? So first, there are various methods which can be used, or maybe the minimize these difficulties. Again I am telling you, we are trying to minimize these difficulties. We are not deleting all the difficulties over there, because still there are lots of difficulties, lots of problems. People or maybe the scientists are still trying to modify this kind of problems, or maybe to solve this kind of problems. So here first one is called the use of chemical hardening agents. So by using the chemical hardening agents, we can modify or maybe solve this kind of problems. Careful selection of wall materials and the solvents so that they should not stick together, so that agglomeration problem can be removed. Addition of parting agents so that there will not be any stickiness in between the coating materials, so that the particle will not stick together. Employing mechanical devices to physically separate the capsules. So after drying, we have to use certain kind of stirrer so that easily the particle can be separated together. There are some kind of additional factors also that needs to be considered to minimize the difficulties during micro encapsulation are formulation of wall material, types of solvents and non-solvents employed, temperature during the process, and the rate of depositions. So these all are the additional factors, or maybe the additional things what we have to taken care while preparing these kind of micro encapsulations. Next, we are trying to discuss what are the main problems generally we are facing that when we are doing some coating of the nanostructures or maybe onto the substrate itself. So first is that the uniformity of layer thickness, that is the vital one, because sometimes we not get some kind of homogeneous layer over there, sometimes we can get the heterogeneous layer, maybe sometimes there I can see some kind of pores or maybe cracks onto the systems, maybe some reach point at that particular point, so that surface roughness is very bad. Sometimes I can get certain kind of agglomerations of the nanoparticles onto the substrate itself, some kind of I can get certain kind of corrosion prevention at that particular point. Maybe I have made certain kind of materials which is not the corrosion resistance, easily that materials can react with the environment, that absorb the water molecule from the environment itself, so that its corrosion can be taken place. Also some kind of hiding the functional characteristics like optical, electrical and magnetic to the substrate itself. Yes, of course, because when I am trying to use the coating materials onto the substrate, simply it will hide the substrate properties, because it will coat all over around. So whatever the substrate properties actually that substrate is having, so it will diminish those properties, only we will get that what the coating material properties is having. Then some kind of optimal weightability problem can be occurred, some kind of chemical compositions like crystalline structure in the nanometer range, that can be a biggest problem at that particular point. And another one is, the last one is called the standardized surface geometry, that different shapes and size when we are making, that keeping the dimension throughout the coating process is very difficult for this kind of nano coatings. So also what the problems we are facing when we are doing the doping of that particular materials. So first, the key challenge for doping nanomaterials is that till now we do not have the high end equipments which can characterize the doping at the atomic level. Yes, of course, whatever the doping we are doing, simple by getting the XPS image or maybe the FTIR or maybe the XRD, we are trying to prove that doping is taking place. But how the doping is taking place, where the doping material is actually going, how it is attaching with the substrate materials, it is very difficult to detect. Not only that, while doing the doping, whether the doping has been done or not, how much percentage of doping has been done, that characterization also is very difficult. So these all are the problems or maybe the key challenge when we are doing the doping of that particular materials. Not only that, this is only our assumptions theoretically that dopant would substitute atom or the dopant goes on interstitial side. Yes, it's totally theoretical based. We are having some kind of softwares by which simply we are proving that the doping is that like lithium doping is onto the interstitial side or maybe the boron doping onto the substitutional side, but there is no experimental validations over there. So simply what we are trying to do, simple from the XPS image or maybe the XRD analysis or maybe the Raman spectra, we are trying to show that that dopant material is present onto the substrate, but it will never give you that where the doping material is actually staying. So here we are doing some kind of assuming that whether the nitrogen doping is substituting oxygen or nitrogen goes on interstitial side. Yes, of course. So in this particular case, when we are doing the doping of this particular material, so sometimes we are thinking that the doping is going on onto the substitutional side or maybe sometimes it is onto the interstitial side, but we do not have any exact chemical characterization by which we can prove that whether the doping is interstitial or maybe the substitutional. Also sometimes it is very difficult to maintain the crystal structure of host material during the doping process. Yes, of course, because it is very difficult to know the particular doping characteristics where the atoms is staying. So after doping it is very difficult to get the final crystal structure of that material. If it is substitutional, the crystal structure will be changed. If it is interstitial, the crystal structure will be changed, but overall material dimension will remain same. So that is why the distorted crystal structure can be formed by which we can get some kind of dope materials with advanced properties, but still the crystal structure of that particular material getting is very difficult. If the concentration of dopant increased by 5%, then it becomes the composite. That is also a vital parameter. But throughout the chemical reactions or maybe that chemical process or maybe at the time of doping, maintaining this particular percentage is also very difficult. Not only that, when I am adding the 1% dopant, 2% dopant, also it is very difficult to prove whether this 1% dopant or 2% dopant is still it is present inside the substrate system or not, or maybe while washing we are losing some kind of dopant materials. So these all are the different problems what we are facing. Also this is also one kind of assumptions that some materials have same valences, so it is difficult to distinguish between the dopant and host material because a metal has more tendency to dissolve into another metal of higher valency. Yes, of course, because when we are trying to do the doping, suppose I am telling that A material is doping onto the B material, then it depends upon the valency of these two materials A and B. So which valency will be higher, that material will goes into the second one. But in that particular case, if the valency of A and B will remain same, then it is very difficult that whether A is going inside B or B is going inside A. So in that case, that is also a biggest problem, that when the valency is equal for both the materials like dopant or maybe the substrate. The electropositive one element and more electronegative the other, the greater is the likelihood that they will form an intermetallic compound instead of doping. This is also one kind of assumptions, because whatever the things actually we are doing, doping has been started very maybe few months, few years back. So this is the new topic to us. Still there are lots of things that we have to see, we have to know, we have to research, because we are having very limited knowledge on the doping itself. So many people are working. So in that particular case, whatever the results actually we are getting, all are on the assumption based, but we do not have any particular characterization tool by which we can prove that which material is doping onto which, or maybe after doing how the materials is look like, or maybe the how the material will behave. Not only that, here also we have given certain example of doping which demonstrates the problem. in case of boron doped graphene, boron have two valencies +2 and +3, carbon as valency is the +3. When boron with +2 valence is used for doping in graphene, it is not possible to dope boron in substitution side of graphene. Yes, of course, because the valency of this particular boron is less than the valency of this particular carbon. So, in this particular case, what is happening, that we are knowing that one valency will be higher than the another one, then the doping can be possible. But if in that particular case the boron valency is lesser than the carbon, that is why the doping will be not possible. But still we do not have any characterization that by which we can prove this one. This is also one kind of vital assumptions while we are doing the doping. Then we can see certain kind of problems during the functionalizations of these nanomaterials. So, the key challenges is that, first is that we can't characterize the functionalized groups at which exact position these groups are attached, whether they are attached at the desired positions or not. Of course, when we are trying to do the functionalizations, we are trying to wrapping the polymers onto the nanofillers or maybe that carbon nanotubes. So, while some lectures on the functional process, we have told that either that material will attach at the end point of these particular nanofillers or maybe onto the some defect sides, but still that is also one kind of assumptions, because we do not have any kind of characterization tools that whether the material is only attached on that defect sides or maybe at the ends or maybe not other places. Then it is difficult to ensure the exact quantity of particular functional groups attached to the nanomaterials. Some basic characterizations which are used to detect the presence of typical functional groups have limitations to detect some of the element or sometimes overlapping in particular peaks, as in FTIR and XPS. Of course, because when we are attaching some kind of materials that is below the carbon, it is very difficult to detect those materials inside the systems itself. So, suppose I am doing some kind of lithium, then it is very difficult to detect that the whether the lithium has been attached to the substrate or not, or maybe the lithium is present to the systems or not, because above the carbon groups, then only it is possible to detect these kind of materials through some kind of characterizations. So, that is a lack of this kind of characterization techniques. Not only that, some reactions control functionalizations is very difficult to achieve to detect particular requirement of functional groups as per applications and the host materials. Not only that, when I am doing this kind of functionalizations, I am doing some kind of chemical reactions, whether that exact particular group has been attached to that filler or not, it is very difficult to detect. So, simple, by doing several characterizations we can assume that this kind of materials has been attached to the systems, but it is not fully confirmed. Next, we are trying to give certain kind of examples of functionalization which demonstrates the problems. Functionalization of quantum dots have several difficulties owing to reduced stability of thiol based conjugations along with aqueous and salt incompatibility, and thus requires more unconventional approach. And also we can do the functionalization of DNA nanostructures. For integration of proteins, a challenge has been the coupling of oligonucleotides to unique position on the protein and subsequent purification of the conjugate. The same thing I am telling once again, that when I am doing the functionalization of this particular material, I do not know whether that particular material is going to the particular site or not, or maybe the functionalization is taking place by this particular material or not. So, here in this particular case, we are showing that when we are expanding the size and complexity, that how the new functional nanostructures is forming, then new generation of DNA walkers. So, here in this particular case, we are getting some in vivo selections and amplifications of DNA nanostructures. So, still I am trying to attach some kind of molecules or maybe the functionalized onto this DNA structure, but still I do not know that whether this material is going to the particular side or maybe the particular positions or not. Then at the end of things that we are trying to say about the surface engineering and its applications. Now, in a brief, just I am trying to tell you that in my lab what we are trying to do, or maybe on which topic we are doing work on, maybe what is our research interest. Generally we are working on the wear and abrasions of these particular materials, which is coming under the nanotribology. Then we are doing some kind of fraction mechanics and fatigue mechanisms of some metal or maybe some polymer materials. Then main thing actually what we are doing, we are trying to do some kind of synthesis, coating and surface modifications of some kind of nanofillers like carbon nanotubes, graphene, silicon carbide, then graphene nanoribbons, carbon black, then carbon dots. So there are various materials we are preparing in our lab. Then we are trying to modify these materials, then we are trying to use this kind of materials for various applications. Then we are using this kind of blending, characterization and compatibilizations of polymer and metal matrix nanocomposites. Basically these kind of materials generally we are using for the aerospace applications, automobile applications, or maybe some kind of other implants. Not only that, polymer nanocomposites for high performance sensor actually we are trying to do. We are trying to use this kind of sensor materials for toxic gas detections. Not only that, nowadays we are trying to use this kind of gas sensors for the dual gas applications, where there will be a mixing of gases and we are trying to recognize those toxic gases over there. Then we are using this kind of materials, generally we have prepared in some kind of nano generator. So by pressing these materials we can generate the electronic maybe the electrical energy, or maybe we are working on the some energy storage applications like the peroxide solar cells, some kind of flowable supercapacitor and the hydrogen storage systems. And here we have done one work on the welding of polymers also, because you know the welding of polymer is very difficult, because we can't put the direct heat to that particular polymer system, then it will melt. So here we are trying to use some kind of vibrational welding techniques by which we can weld different polymer together. Then we are using some kind of non-conventional machining process in terms of electrodeposition machining and the surface finishing process, some kind of advanced surface finishing process, and we are also working on the biopolymers, say for the targeted drug delivery, some barrier applications and some kind of food packaging techniques. Not only that, nowadays we are trying to make certain kind of magnesium alloys which can be used for the orthopedic implant. So here this is my whole team. We are working in the advanced composite lab of IIT Roorkee. So this is myself. Here these two are the main backbone of this particular lecture, or maybe that whole lecture. So one is Mr. Binay Panwar and another one is Ms. Kirti Rati, those who are working as a TA1, teaching assistant 1 and teaching assistant 2, and these all are my group members, including these two, namely Subhas Singh, Souvik Bagh, Jitendra, Pushpendra, Nidhi, then Navjot, Farhan, Tushar and Manmeet, by whom that we have made this kind of lecture in front of you. Thank you.